Nanotechnology is one of the hottest areas of science today. And it isn't exactly new. If you think about it, every one of the cells in our bodies actually contains organelles that are operating at the nanoscale. Even manufactured nanomaterials are not new. For example, during the First World War, the first commercial tires reinforced with nanomaterials were introduced, and that nanomaterial was carbon black. But what is new is that we're starting to be able to design these materials in a principled way from the bottom up. So for example, today one of our speakers, Dr. Michael Saylor, will talk about smart dust, which he has invented. You'll also hear from Professor of Chemistry and Biochemistry Andy Kummel and his colleague Brad Messmer from Moore's Cancer Center. And they'll discuss a medical application of nanotechnology. But first we're going to have Professor Schuler with us in person to talk about what happens when things get small, what is some of the interesting physics behind that. So please join me in welcoming Professor Schuler.
Thank you very much. I will tell you about nanoscience. I will not tell you about technology, and this is one of the first things that I would like to emphasize, especially to journalists, because there is always a confusion between always switching from science to technology, and invariably what we get is questions about technology and not questions about science. So what I would like to do is I would like to emphasize to you that this is a science, and the science is actually different than technology. The motivations are different. They may lead to applications, they may lead to interesting things, but actually science is not necessarily motivated, nor it is geared towards directly producing something useful. This is not what we usually do. So nanoscience, as you can see, the reason I have this picture here, this is a picture which is very appropriate for UCSD, because that's a picture of Dr. Zeus, who actually is close by here, and because Dr. Zeus is one of these books that I discovered in my garage in among one of the old books. Dr. Zeus actually was running around with these things measuring length scales, and that's what all nanoscience is about. It's about seeing what happens when you measure length scales, and when things become smaller and smaller and smaller. So the other thing that I hope to convey to you, this is a problem that we physicists have, I myself in particular, is that physics is entertaining, that physics is fun, that is important, and that it is useful. But therefore it's the best profession you can possibly ever have, okay? That's what I actually am hoping to convey to you. So physics, you see, is like magic. This is what I would like to convey to you in this talk also, that physics is like magic. For instance, you see here it is, this is from a movie from Harry Potter. There it is, you see, there it is a magician, you see. He has a beard, I have a beard. You see, it's like magic. You see, you guys probably all came here in a broom. The broom was slightly bigger, but there it is, a guy on a broom. You see, flies on a broom, you fly on a broom. Okay, there it is. You see, there is Harry Potter with his magic wand. Here, see, I have a magic wand. I have a red one. I have a green one. I have all kind of colors. So this is even better. You see, so I am really like a magician. All right. Okay, so you see, I can't go away without telling you about physics, and so I have to tell you about physics. You see, this is what up to about the 1900s we were using to talk about physics. These were the so-called Maxwell's equations. This is what is called classical physics. See these Maxwell equations. Now I'm going to tell you about each one of these terms. Okay, for instance, I'll tell you about this term here. See, that's a minus sign, and that minus sign shows you how magical physics can be, and that's why I thought I'll make a magic trick here for you. And so I'm going to, not only that I'm going to make a magic trick here, I'm going to put Sherry on the movies here. So Sherry, why don't you come here and help me? I need a helper here, okay? So Sherry will help me with this magic trick. Sherry, you will swear that this is a carbon tube, right? It's nothing but a tube. And you will also swear here for everybody. I don't know you, right? I never met you before. Okay. You can also swear that I have two plugs here, right? They are all identical plugs, right? Yes. They look the same size. I really can see through this. You can see, and there is nothing in there, right? Okay, so and these two plugs are, and they kind of fit very loosely in here, very loosely fit in there, right? And they don't stick to this thing at all, right? Neither of them, right? So what I will do is just put your hand under it, and I'll just drop this one, and you'll see there it is. This will drop through it, right? It drops through it, right? Very easily. Right, you agree that it drops through it, hold it again, let's just hold it again, so it drops through it, there it is my other plug, right? It drops through it, no problem, right? This is a real magical trick, okay? Now I'm going to show you the real magic. So here is the magic trick, you do the magic trick yourself, okay? You drop that in there, it feels very sluggy in there, well, she broke it. It doesn't fall through. You see that something happened, okay? It's magic. It is really magic, you see? It's all it has to do is with that minus sign. Up, you see? Throw it again in there, and it takes a very, very long time to fall through. That is because it's magic, because these equations, that minus sign in particular, tells us that the way this should fall through is like that. Thank you, Sherry. Please give her an applause. She deserves the applause. Okay, so that is how magic works. The reason that you're not accustomed to seeing this is because you don't see the magic that there is behind these equations. We can see it, you cannot. Or you think you cannot. Actually, you spend enough time, you can also see it. So, okay, here it is the basic question that started all this business, in fact, I believe, all this business about nanoscience. Can one control the movement of an electron using an electric field? What does that mean? An electron is a negative charge, and the question is, can you control its motion with a battery? So here it is, these electrons, they're moving around. There is a battery that is put between those two yellow plates, and there it is an electric field that is pointing that way. And you see, if I point the electric field that way, the electrons go up. If I point the electric field down, so that I call it a positive electric field. If I point the electric field the other way, the electrons go down. And this was sort of a fundamental question. There was no applications that anybody saw for this, actually, asking, can one control the motion of an electron with an electric field? And the first person that asked that was an American scientist. His name was Lee De Forest. And Lee De Forest invented this device. This device is this device. It was called an audion. Later on, much later on, it was called a triode. Okay, it's this device. You see, it looks just like the drawing there. You can see it, okay? It consists of a center source of electrons, that red thing there. You can't see it here because it's blocked by this thing in between. And then there is a collector. So the electrons go away from this center source there, and they go to that blue thing. Okay? And the question is, can you control it by putting something in between? Which is something called the grid. The rest of it, you see, that rest glass thing is there to keep those peanuts, to keep the rest of the atoms in the world outside here. So that only the electrons move inside there. Okay, so this was the question. Lee De Forest, actually this American inventor, he invented this in 1906. There it is, a picture of Lee De Forest. He really looks like he was in 1906, you see. Sort of looks like my grandfather. And so then came the question, so here it is what all this solid state physics is all about. You take these atoms, and then you take a solid there, you put a battery across it, and you move the electrons inside the solid. And so the next question that was asked is the following. Can one do the same inside the material? Not in vacuum, but inside the material, okay? So that was the question that we were asking. There are our electrons going through the material. So here it is the basic question. Can one control the movement of an electron inside the material using an electric field? The same thing we put to a battery. Can we control the motion of these electrons in there? Okay? And so this gave rise to the most important invention of the 20th century. So can anybody more or less name any of you guys are journalists. Does anybody know? Anybody has a guess? Yes? The light bulb. Okay, that's a good one. I don't think it's the light bulb, but light bulb is a good guess. Does anybody have any other guess? Good, very good. There is somebody that I paid off. Who's the person that I told? Yes, okay, good. The gentleman there. This is a transistor. This is the first invention of the transistor. Now remember, when Lee De Forest invented his audion, a person in the Himalayas didn't know what the hell was going on down there below the Himalayas. This transistor is what allowed the person to go up in the Himalayas and figure out what's happening downstairs. That's the invention of the transistor, this ugly looking thing. You see, and this was invented by 3 American inventors, Bardeen, Shockley, and Brittain. They got the 1956 Nobel Prize in Physics. Okay, so that's the invention of the transistor. What that allowed us to do is to take this tube, the audion, this big tube, and shrink it to a tiny little size of about 1 millimeter or something of that sort. Okay, so that's what allowed us. And that, remember, taking that audion and making it that small, what it allowed us, that the person that goes to the head or to the top of the Himalayas could communicate with the person that is down. So communications basically invaded the world. So that was the invention of the transistor. The next invention was the following. Taking the transistor and taking 1 million of those transistors and putting them on something like this. Okay, so this is stolen from one of my old friends. This is from a PDP-8 computer. And what this allowed us to do is to control many processes that we have in the universe. For instance, to control many of the medical machines that you have, control many of the communications that we have, this sort of computer. So this was 1 million of those transistors are put into this. Now, taking 1 million of these and putting it onto this. So this was from a computer of a friend of mine that he is not working today in the morning because I needed this to show it to you guys. Okay, so this is taking 1 million of those and putting it into this allowed us to invent the internet. You cannot look at anything today, any library or anything, if you don't have this kind of shrinking of things. So now, you see, each one of those inventions, shrinking things 1 million times, allowed us some major invention that we could not have predicted from the beginning. So what I will tell you now about is what is the science behind taking this and taking 1 million of these and sticking it into something the head of a pin. We don't know really where it's going to lead. But surely the revolution that will happen in technology and in science will be comparable to what happened, what I showed you until now. Every time we shrank something 1 million times, something fantastic happened. Okay, so why is this important? When things get small, things are very different. See, this is what it is very difficult to understand. When things get small, the physics and the equations and the science that governs that behavior is very, very different. It's not like what we are accustomed to seeing. So how small are we talking about? So here are these magnetic dots. These magnetic dots are comparable to sizes that you have inside a cell. So when things get small, then we use this equation, this is the so-called Schrodinger equation, and you see this Schrodinger equation is really magical. Behind this Schrodinger equation, there are as many magic things as there are behind that Maxwell's equations that I told you. And so what do we see behind it? Well, here it is what we see behind it. See, there it is a radio. And we see behind it that there are not little men playing jazz in the radio. There is something else there, the way it plays jazz there. Let me show you, for instance, another thing that is very magical that comes out of all this quantum mechanics. This thing. This is fantastic. This is a guy, his name is Röntgen, Nobel Prize of Physics in 1901. He invented the X-rays. In fact, in Europe, these are called the Röntgen rays because of his name. And this is fantastic. We can look inside your body without having to cut you up. But it's even more fantastic than that. You see, this guy managed to do something that I have never managed to do in my life. He managed to convince his wife to put her hand under this thing. You see, that is his wife, and that's her ring, you see. I haven't been able to convince my wife of anything, you know. See, here it is. He convinced her to do this, okay? So this is fantastic. So this is what Schrodinger equation allowed him to do. Here is another thing. If I would have told you 25 years ago, I will be able to look into your mind, look into your head, and see the way you are thinking. We're almost there. We actually can see certain parts of the brain lighting up, and the phenomena by which we do this is by the so-called nuclear magnetic resonance. This word is dropped invariably because the word nuclear is not very popular anymore. So it's called magnetic resonance imaging, but in fact it is nuclear magnetic resonance. Was invented by, was given the invention of this thing were two physicists, Bloch and Purcell, Nobel Prize in 1952, and then very recently, Lauterbur and Mansfield also got the Nobel Prize for actually making this machine, making a machine out of this so that you can look inside the brain. And actually here at UCSD there is a center for magnetic resonance imaging somewhere down Gilman Road, I think, okay? So, you know, the magic that I work on is this particular magic that you saw in the movie, which is the magic of how things go through walls. And what I wanted to show you there in that movie is actually that things do go through the walls. They don't go above the wall. They go in between the atoms. They go through the wall by this phenomenon called the quantum mechanical tunneling. Okay? And you use it every day. You use it every day. And believe it or not, you yourselves are using it because none of your computers would be working. So your read head, the thing that reads the information on your computer, uses this phenomenon of tunneling. And just 5 days ago, Freescale actually has recently introduced a non-volatile memory for telephones, for cellular phones, and for when this will perhaps be used also in computers, so that it doesn't, basically these non-volatile memories, once you turn it off the phone, it stays the way it was. So it keeps the memory without disappearing, without having to supply it with a battery. And it just was announced last week the non-volatile memory is actually the commercial use of tunneling. And there it is, you see, it relies on the same thing. On something, there it is, the wall. You see that yellow thing? It's a wall. It's electrons going through that wall. And so basic research pays. That's what I want to tell you. When people started studying tunneling, it was not clear what it is good for. It was just one of these curiosities of science. And very unusual. You throw an electron to a wall, and instead of going above it, instead of going in between the atoms, it goes through it. And that now, it's into read heads. You use it every day. It probably will be into telephones as soon as these guys manage to make some money out of this. Okay, so I hope that at the end of this talk, I will just end up, and I'll end up just on my 15 minutes, which I was allocated, I guess, that physicists are entertaining. This is how I started. That physicists are fun, and that physics is very important, and physicists are very important. And physics is useful also, but we don't know where it is useful. This is what I want to tell you. Science is generally very difficult to predict a priori where it is useful. And the most important thing that I want to leave you with is that physicists are very good looking. And so you can see there is a bunch of pictures of a bunch of physicists being good looking. Thank you.
You heard a lot about electrons and magnets, and what we missed in that is, or one of the areas of science we missed in that last presentation is optics, how light is used. And I'm going to talk about how we harness optical properties at the nanoscale. And I'm going to use kind of two general touchstones, or technology touchstones. One is in sensors, and the other one will be in medical devices. And I'll start with this picture here. This is a picture of our smart dust. What you're looking at there looks like a little ball of lava. It's a water droplet, and to get an idea of the scale, you can see there's a syringe needle here. This is a kind of needle that would be used in a doctor's office. And that's just a droplet of water, but it's sugar coated. It's coated with little particles of silicon, and they have these really pretty colors. And I'll spend a little time talking to you about how we make these pretty colors and why we would use these and why you'd care to have these sticking to a ball. I'm going to start with this image. The immediate image you get from looking at a pile of dead fish on the beach is different than what you would get if you're walking on the beach and you see one dead fish. You jump over it, you walk around it, you don't think anything of it, and you keep going. It died of natural causes. These are not natural causes when you see a pile of fish on the beach. And so if you think about it, these fish, although they didn't really intend it this way, these fish were acting as sensors. And they were sensors in the field. They were not, they didn't have to take the sample of water back to a lab to figure out that there was something bad in the water. They just saw a bunch of fish piling up on the shore. And in this particular incident, this is a cyanide spill from a former Soviet Union mining camp that got into the Danube. And then the first indication they had that there was something wrong was that the water, had killed the fish. They saw a bunch of fish dead on the beach. Right now, we don't have early warning systems in our environment, typically. In this room, we do. We have a smoke detector. If there's a fire in this room, we'd probably all know it, and we wouldn't really care that the smoke detector the alarm was going off, because we would know that something's on fire in this room, but it would at least allow the fire department to get a little quick early warning that they should come here and put this fire out. And that's really one of the things we'd like to have out in the environment, in the open field, and we just don't have that. If you go swimming, you go to the beach, you'll find that there maybe a couple of days later you might find that there was a bacterial spill in the water, and you might get sick from drinking some of the water. How do they figure out that the water is toxic? Very much similar to this incident. They see something's wrong, or they suspect something's wrong. If there's a heavy rain recently, then they'll go take they'll take a sample of water out of there, and they'll do what they call a grab sample. Take a sample of water, you put it into a bucket, label it, attach a GPS code to it so you know where you took it, take it back to the lab, and do the analysis. And this takes time. And so what would be great is if you had a bunch of fish sitting out there in the field, And maybe they weren't fish, but maybe they were something that you really didn't care about killing, like a little sensor. And you have them tell you or communicate to you that there's something wrong. So this is the general area of what is now being referred to as wireless sensor networks. And in fact, in this room, there's a network of sensors that's similar to what I'll be talking about in a second. Everybody here probably has a cell phone in your pocket. And maybe you turned it off before you came into the lecture. Maybe you didn't. But that cell phone's acting as a network. And it's talking to a repeater station. And somewhere, somebody knows where you are. Or at least they know where your phone is. And your phone is communicating with that repeater station. And you can use that phone as a sensor. It's sensing essentially where you are, at least telling the network where you are, so the phone call gets routed to you. And you have a sensor located in that cell phone as well. You, of course, probably have a video camera in it. You also have a little thing that gives you the number of bars. It tells you the signal strength. That's sensing something local about your environment, something that you care about right now, whether you're getting reception or not. And we have ability to shrink these types of things, these little cell phones or radio devices, down to something that's on the order of the head of a pin. This is really one of them. This little thing here is a small wireless device. It doesn't have a battery attached to it, but it has pretty much everything else it needs to operate. And they can make these things very small. Okay, they can make it much smaller than your cell phone. And what we have, and then you heard in Ivan's talk, you heard a lot about the evolution of electronics and how that's been shrunk down. And one of the advantages that we've received from shrinking electronics down is we can make radios this small. We can do very effectively the wireless part. We can communicate. We can put a computer on that chip. We can do the data processing. We can network these things and they'll talk to each other. And we have the protocols and the computer programs that allow us to do that. But what's really needed still is the thing that kills the fish, or the thing that tells the fish that something's gone wrong, and that is the sensor. Okay, right now we have a smoke detector in this room. That's a sensor. That's a very robust sensor. It'll operate for years without having to be replaced. In small devices, we don't have really good sensors right now. We have a few things that we can do. We can measure light intensity, so we can make cameras and shrink them down very small. We can measure temperature. We'd really like to be able to measure chemicals and biological compounds, and that's one of the areas where nanotechnology comes in, because to be able to build a sensor that small and to place it into the world of silicon electronics is a big challenge. And I'll show you, I'm going to show you some movies here of little nanosensors. This particular sensor here is a little green chip. And I've got one here. Let's give you an idea of the size. So this is a silicon wafer, and it has a color to it. It's that particular color is green. And what's going on in this experiment is this is sitting in a chamber, and it's being dosed with acetone. Acetone is a chemical. You're familiar with it. It's fingernail polish remover is one of the uses of acetone. And what's happening is that vapor, the fumes from that acetone are being introduced in this chamber, and you can see very clearly that there's a color change from the green to the red. And what's going on in the movie is occasionally it gets pumped out, and so that was when the color turned back green. And so this is a nice little sensor because it's small, it uses zero power, and when there's a chemical in the air, it turns red, big stop sign. So it's good mnemonic. How do you make something like that? It turns out that to get that to operate, to get those colors, requires you to operate at the nanoscale. The device itself is not nanoscale, but what's inside it is. And this is a little chemical experiment. I'm showing you two experiments today. This is the second one. And this is just how you would make this nanostructure. And what's going on in that little experiment there is there's a silicon wafer, and those bubbles forming are a corrosion reaction that we're turning on with this electricity, with this wire loop that you see there. And that is drilling out very small holes, nanometer scale holes in this silicon wafer that generated that little chip. And when you're all done, you get a structure that has very fine layers to it. You can kind of see the layers in this picture here. This is a cross-sectional image of one of these little colored chips. And it has bands, a layered structure to it. And that layered structure, it gives you this green color that you see in that chip. And it seems really sophisticated and complicated, and you might wonder, well, what's going on here? In fact, this is a problem that was solved by nature eons ago. That color comes from that nanostructure, but it's a nanostructure that can be built by nature as well. And one of the best examples of this type of a nanostructure is in a beetle shell. The biologists have this term they refer to as structural color. The leaves on a tree are green because they have molecules in them. The molecule is chlorophyll. That's one way that nature can make color. It can build a molecule and make a colored structure, a pigment. The beetle can't afford to do that. It can't grow a green molecule into its shell because that green molecule can bleach and change color. And so it builds a more robust form of color that's akin to how rainbows have their color and thin soap bubbles get their color. They have a structure. A soap bubble has a very thin film, and the iridescence in that soap bubble that you see comes from interference of light in that film. The film itself is clear, but if it's thin, on the order of a few wavelengths of light, then it imparts a color to it. And that's what the beetle does. It grows a nanostructure. In the case of the beetle shell, this is no longer silicon now in the structure I showed before. This is chitin. It's a biopolymer that the beetle builds. And the cross-section of this beetle shell would look like this, and it'll have layers of chitin alternating every few hundred nanometers. And that structure then gives rise to this color, similar to how soap bubbles get their color. And so the green color you're seeing here in the shell of this beetle and the red color here, these two colors are derived from a structure in the beetle shell that's not a pigment. It's like a soap bubble. And that's the same type of a structure that we build in these silicon materials. What's different from the silicon that the beetle doesn't have is that the silicon has holes drilled in it. There are pores. And so you can put things into those pores. And this is an example of really what happens. It's relevant to the movie that I showed. These are now small particles. Let me see here if I can get this movie to play. Okay, so these are small particles made out of that chip. These are now on the order of about the diameter of a human hair. And you can see that the particles started out green and they turned red when we put molecules into those little porous sponges. And this is our smart dust. This is a material that can change color when it sees a gas or a vapor. And this vial gives you an indication of kind of the size of these particles. Now we've made a sensor, something that can change color, can detect a gas, and it's small enough to be able to be placed into an electronic device. One of the things you can do with these things is you can make them into sensors that can be seen from a distance. And so this has led to the idea of not wiring up your sensor, not actually having it plugged into the ceiling like a smoke detector would be, but dispersing it in the environment, painting it on walls, putting it on buildings or maybe on people on clothing, and having it travel through the environment and do sensing. And this is an example of kind of a notional scenario, an idea, an artist's conception of how these materials could be used out in the field. Little particles that change color when they see gases could be read from a distance with a laser beam. And as you see the color change, those particles are encountering a gas, like a volatile organic compound, a pollutant, or maybe even a toxic chemical weapon that's been dispersed by a terrorist. And so that's kind of one of the application areas. And again, it kind of goes back to the fish. You have lots of these things out there, and if one or two of them changes color, it might be a false alarm. But if all of them change color and you see them all washing up dead on the beach, turning green to red, that tells you that there's something serious there that you've got to deal with. So that's kind of the idea of sensor networks. Where can you go with a sensor? We talked about putting them in the environment. You can also put these things in the body. And what you're looking at here is an image of a live rabbit's eye. You're looking through the iris, and this is the optic nerve in the back of the eye here. And this little series of corrugations are a needle track. And these particles, there's one of the green particles sitting there inside the eye of the rabbit, and that was the needle track. It was just recently injected into the animal right before this picture was taken. And the concept here was one that Bill Freeman really came up with. He's our collaborator in the Jacobs Retina Center here at UCSD in the Eye Center. And it was the problem of, or the challenge of treating a patient who doesn't necessarily know that they're going blind. His disease that he works on is macular degeneration. And this is a disease that typically is age-related. That older people will get this disease and they'll slowly go blind. And there's no good way to treat the eye. The eye has a barrier similar to the blood-brain barrier. And so you might think that, well, let's just give the patient a pill every so often and it'll kind of treat this disease. If we had pills like that, it would be great. We don't have them. And one of the reasons we don't have them is because those most medications won't pass the blood-eye barrier. The eye is a very protected area in the body, and it won't let things in. And so they have to actually stick a needle into a patient's eye and inject a drug and leave it there for hopefully up to 3 or 6 months before they have to re-inject the patient. Ideally, you'd want to inject the patient once a year or never, but the minimum amount of time of injecting is important because then there's less chance of infection. And so the sensing aspect of this thing became important. You know, I told you these things can change from green to red when they load or unload something. And so the idea is to load one of these nanostructures with a drug, and then the doctor can look inside the eye and see when the drug has come out and when it's time to re-inject the patient. So they don't overdose the patient and they don't underdose them either, because one of the problems with medications is everybody's different. And so being able to look into the eye and see this little microsensor telling the doctor that they need to re-inject the patient was a key aspect of using these little particles in the eye. And so again, the concept is that you have what we're now referring to as a mothership for nanotechnology, something that can deliver a payload, a drug in this case, and in the body, and that you could be able to monitor this thing. So when the drug is loaded into the eye, or the particle is loaded with a drug, it has a certain color, and then you can see that color change as the drug is released. So that's an interesting aspect that you wouldn't use with a beetle shell, but you could use with silicon. This next couple of slides, I'm pretty much going to finish up here, are just serve to introduce some other aspects of how we could use nanotechnology in the body, and they'll introduce the next set of talks that you'll be listening to. This concept is, okay, we can inject it into the body and leave it, let's say, in the eye. Can we put a particle or maybe a nanostructure into the body and have it circulate through the blood system? And in this case, now we're trying to find tumors, cancerous cells in the body. And the diagram here is kind of showing the artist's conception of what we'd want to do. A nanotechnology device that's circulating through the bloodstream and then lodges itself and locates itself close to tumor cells and then does something for us. And the thing we want it to do is to maybe sense that there's a tumor there, or destroy the tumor, self-destruct. Just diagnose it. Tell us that this patient has a tumor before it shows up on an MRI or an X-ray scan. When the tumor is too small to be seen by normal technologies, maybe nanotechnology can see that tumor. And if you can treat the patient earlier, your chances of survival, the patient's chances of survival are much better. And so to do that, we really need to build some very sophisticated devices, devices that really rival the technology and the sophistication that you have in naturally occurring systems like viruses and bacteria. They have to be able to swim around in the body. They have to go find the target. They have to attach themselves to the target, and that requires us to have what we call targeting moieties. And then to activate something, when they found that, to either activate it to release a drug, a therapy of some sort, or tell us that they've seen that tumor. And so that'll introduce the next series of talks. I think we're going to be talking now more about nanomedicine and nanotechnology used to treat medication. So thank you very much.
About 2 years ago, the National Cancer Institute at the NIH, the National Institutes of Health, put out an initiative saying that cancer research seems to have run into some problems or run into sort of some dead ends with conventional approaches, and that this emerging science of nanoscience and nanotechnologies that you've heard about seems to have some promise for dealing with cancer. And so in response to that initiative, UCSD began to prepare a proposal, and I was fortunate to be part of that and got the opportunity as a biologist to start having these conversations with the chemists and the physicists and various other people involved in the technology. So So I'm going to kind of give my half of the conversation of trying to explain to you, and as we did to the engineers and the physicists, really what cancer is and where our problems are and where we think nanotechnology might offer some promise. And then I think Andy's going to sort of have his side of the conversation and show you where they're making progress and where we're now working together to do that.
And we're here not just on behalf of our own labs, but UCSD has a very large grant called for nanoscience for cancer research, which must involve 20 faculty, including both Mike Saylor, Ivan Schuler, Roger Chen, and Pat Jennings, myself in chemistry, and many other people. And so we've been stealing slides from many of these people to show you some of the ongoing research in the use of nanotechnology in cancer at UCSD. So this research is ongoing. We even have some clinical trials going on now.
So I'm going to give you just a quick introduction to cancer and particularly try to highlight a few central concepts that I think are important for what Andy's going to discuss. So this is kind of a schematic of what happens in cancer. So it starts from a single cell, and this is one of the cells in the body. If it's a lung cancer, it'll be a lung cell. And this cell goes a little loopy and starts to divide somewhat uncontrollably. And it accumulates cells, and this is an exponential growth. So one cell keeps growing, there's 1,000 cells, and then you get a tumor, and this tumor keeps growing. And then down here at the bottom, the real problem is once that tumor is able to spread to the rest of the body, if left untreated, that'll usually cause the death of the patient. So this process can take years, and where we currently stand in cancer medicine is that we can see a tumor on X-ray somewhere in this scale, which is about 100 million cells. So by the time a tumor can be seen on X-ray, there's already 100 million cancer cells, and that's a lot. And that presents a challenge to treating that tumor. And even worse is if the tumor is not seen on X-ray. For instance, if a woman's conducting self-exam on a breast and notices a lump, well, that lump is probably at least 1 billion cells, because it's got to be that many cells for it to even be possible to feel it. So we're playing very late in the game right now. And even if you have a therapy, let's say, that's 99.9% effective, that sounds great. Well, all that really does is slide you from here back up to here, and you're still dealing with an enormous amount of cancer cells. So one thing that we want to do with nanotechnology is see if we can start playing up here and deal with the tumors much earlier, as Mike sort of alluded to. And as you'll see, these numbers, actually, there's going to be a lottery analogy later that's going to play on that. So what's happening is, or actually the way this is, the previous slide is it's a little deceptive, because here we call it malignant transformation, like one thing happens and boom, now that cell's cancer. That's not really how we think it progresses. So cancer is an evolution, and by evolution I mean that there's many changes that are occurring, and then there's growth of those that have the right set of changes. And these changes and cancer is a genetic disease, so these changes are occurring in the DNA of the cell. And those changes kind of come in one of two flavors. Either you turn on a gene that will help the cell grow, so a gene that promotes cell division, or you turn off a gene that we call tumor suppressors that stops cell growth. So the cell kind of has go signs and stop signs, and either you turn on the go or you turn off the stop. And in fact, usually what's going on in cancer is not just one of these or just one of each, but a combination of these two different types of DNA changes or changes in these types of genes. And cancer can then result from a combination of these changes, and that combination is there's probably many different combinations that can give rise to a malignant tumor. So this gives rise, I think, to 3 major challenges in cancer where nanotechnology is going to play a role. So from our perspective as biologists or medical researchers or physicians that are treating cancer patients, one of the big challenges about cancer as compared to other diseases is that it comes from our cells. So I'm going to use the term, it's a domestic terrorist. It's grown from us. The other problem is that cancers are very different from patient to patient, so it's that combination can be very very complicated, and we don't always know, even though 2 people each have lung cancer, a drug that works on one may not work on the other. And then cancers also continue this evolution throughout their course, and they're continually changing. So I'll go through these a little more thoroughly. As I said, the first major challenge with cancer is that it comes from us. It comes from one of our cells going crazy. And so I'm going to contrast that, let's say, with a bacteria or a virus. So a bacteria or virus is like Martians landing in your body. I mean, in terms of the molecules that are present, it's very different, it's very easy to identify, and it's very easy to treat. So our immune systems do a very good job of recognizing bacteria and viruses. We can make drugs such as antibiotics that will kill bacteria very well but are virtually non-toxic to us. Whereas in cancer, again, it's one cell, and that cell's not just grossly changing, but having all these little changes. So there's not necessarily one thing. So out of a crowd of people, maybe one of these is a domestic terrorist, but you'd really have to look at their bank records and their internet chats and maybe their phone records to be able to even come up with enough evidence to figure out who it is. And that's very much the problem in cancer, is that even figuring out what really is the tumor cell, it's not just one thing, and there's a multitude of different changes that need to be detected. And right now, we really don't have ways of doing that. So that's probably the major challenge, and but also leads into this one, which is that all of those changes are going to be different from person to person or tumor to tumor. So one way to think of it is that each tumor is kind of like a salad from a salad bar. So if we all go out to lunch and there's a salad bar, we'll all walk up and make a salad, but each person's salad is going to be a little bit different. And some may have tomatoes, some won't. Some may have more tomatoes, or the ratio of cucumbers to tomatoes is going to be different. And we don't always have good even ways in cancer of even knowing what's in the salad, but we might know a few things. So we can measure whether it has a tomato or not. And the problem that this presents for therapy is that many drugs try to target, the cucumber or the tomato, and that's not bad, but if a salad doesn't have a tomato in it, then a drug that goes after tomatoes isn't going to be very effective. And a good example of this is the drug Herceptin, which is used to treat breast cancer patients. It's quite effective. The problem is that it only works on 20% of women that have breast cancer. So that's like the tomato in the salad. So if the particular cancer has that target of Herceptin, it works, but 80% of them don't have it, and so that's kind of a useless drug. And this is a huge problem that's constantly rearing its head. So when the clinical trials are done, 20% or 30% of people respond to a therapy. A lot of the times we don't know what the tomato was or what the cucumber was, so we don't know, is the drug just not that good, or is it really good for a subset and not good for other variations of the salad. And then the third challenge where nanotechnology needs to come into play is this idea that the cancer is continuing to evolve. So you can think of a tumor as kind of playing the lottery. And if any of you buy lottery tickets, the odds of winning that lottery are pretty dismal, usually 1 in several million or 100 million, which sounds like it's not such a bad problem. But if you remember from this slide, as this tumor grows, this is like, when there's one cell, that's like the tumor buying one lottery ticket. That's probably not going to win. But if you buy 1 billion lottery tickets, well, you're going to win probably just about every time. Certainly if you get up to 10 billion, 100 billion, you're going to win many times over. So as Mike alluded earlier, this problem of early detection is actually huge. If we can play with tumors or see tumors and attack tumors down here, we can get them before they've found the magical combination that makes them nasty. But if we are here, it's much more difficult to deal with. And so that means that what we want to be able to do is see tumors early and also be able to detect if therapies are working to push this number back up into this region to be able to monitor that. So I'm just going to briefly tell you one project that our lab is actually involved in. So one idea that we've had, and Andy's going to elaborate on this element a little bit more, but one thing that tumors have to do is they have to provide themselves with blood. So this mass of cells grows, and it needs blood vessels to keep it happy. And tumors, it's one of the changes that occurs is that they trick the body into making these new blood vessels. But tumors aren't perfect, and so they often have areas within the tumor that aren't getting enough blood and that are being starved for oxygen, and those cells start to die. And when those cells die, they release molecules and proteins and enzymes that the immune system can actually recognize. Now, this immune response doesn't really help cure the cancer or fight off the tumor, but we think we can use that as a way to use the body's own detection as a readout for the presence of a tumor. So what we're in the process of doing is doing this experiment where we take serum or blood from cancer patients, and then we label the antibodies, which are the immune molecules that recognize these particles. We're going to label the cancer ones with one fluorescent color, and then we're going to take normals and label them in another color. and then we're going to mix them with this library of peptides, which are very small molecules, and we have 1 billion different peptides, each on a little nano bead, and so we're going to mix these all together, and so the antibodies in cancer will bind to some of these little shapes, and the antibodies in normal people will bind to some of those shapes, and in some cases they'll bind to the same shape, and that's no good because it doesn't distinguish, but there's good evidence that we're going to find a lot of shapes that bind specifically to cancer antibodies that have been produced by cancer patients, and then these down the road will collaborate with our colleagues and make into nanosensors or nanoarrays and have ways of detecting cancer, hopefully much early, relying on the body's own natural amplification system rather than necessarily one of these cool devices.
So one of the people at UCSD who's been working for a very long time upon trying to detect cancer cells has been Roger Tsien, who's one of our most famous chemists. And what Roger's been working on in his group is basically finding molecules or making molecules that enable imaging agents only to go into cancer cells. And what it is he first figured out that, well, all these cancer cells are so different. So if you want the imaging agent to go into cancer cells, you need to find something that they have in common. And it turns out that his lab did some experiments and found out there was a particular type of protein that was given off by many cancer cells. And then what they did is this thing here, which is a payload, is a fluorescent imaging agent. And they attached it here to a positively charged molecule that enables these payloads to go in cells. And then they also put in this green linker region, and then this red region here, which is negatively charged, that prevented this payload from going in. So these things are circulating around in the blood. They won't go in cancer cells or any other cells until what happens is this enzyme, which is given off by cancer cells, this type of protein, comes along, and you can see how it snips this. So this green region gets snipped by a molecule given off by cancer cells, and then it can go inside. And so what Roger's lab did is they took a human tumor, because they wanted to see if this really worked on human tumors, and they put it inside the mouse. So this is the mouse here. It's alive. You can see it's lying on its back, okay? And then this tumor is right near the skin, so they can image this with lasers. And then what it is that what they did is they injected one of these things that had one of these special linker molecules into the tail of the mouse, and it allows the tumor to light up. If they just put a random linker in here, not this very special one, you can see how the tumor doesn't light up. So this is a great thing, because this is the first step in trying to find molecules that enable you to put these payloads into cancer cells. The first step is imaging, and obviously the second step would be good if you could put an anti-cancer agent on. But this is a pretty dramatic example. And as part of our Nano Cancer grant, what Roger's trying to do is basically to get particles near cancer cells to start to stick together. So they get a whole bunch of imaging agents very, very close to cancer cells. Because when you get all the imaging agents very, very close to the cancer cells, they're easier to see. And he wants to use nanoparticles because big particles have a hard time getting into cells. So what it is he's doing the same basic trick here, is he has these particles here that don't stick to each other, but then what it is this protease, an enzyme that's given off by tumor cells, causes these red things all of a sudden to become sticky, and they agglomerate together here. And so the idea is that we could put these particles into the blood and start to image very small tumors. So like as Brad said, the trick is to find the tumors when they're really small, because by the time they're huge, the cells are so diverse, there's so many of them, one of them is going to be something that's going to kill you. This is a movie from Dave Cheresh. So Dave Cheresh's lab, what it is, has been developing particles that kill off this process called angiogenesis. So Brad was alluding to this. So one of the big problems in cancer is even if they find the primary tumor, you have the metastasis that can kill you. So you hear about women who have breast cancer, but they catch it too late and the cancer spread. And the question is how do you change things around so that metastatic cancer is not a death sentence? And as Brad said, the problem is by the time the cancer spreads, it's very diverse. So it's hard to have one molecule that goes after all cancer cells. But it turns out when the new tumors start, they need blood vessels to feed them because the cells need oxygen. And it turns out those blood vessels are different. And Dave Cheresh discovered there's a protein on the surface of those new vessels that come out. So what it is he has these particles here, and these are these special vessels that feed the tumor, and they have proteins on the surface. And can you see how these particles only stick to these special vessels? And that's because those special vessels there have that special receptor for the ones here, and then these things carry a payload, which I'll explain in a minute, and it kills off the vessels. If you want to kill off all the tumors, cut off the blood supply. This is the particle that Dave has used in his studies. He has over here another particle, and what's so important about this particle, it has these green things on it, and these green things are a molecule that sticks to that protein that was only on the surface of the cancer vessels. And that's what he discovered, this alpha V beta 3. And then what he wants to do is he wants to kill off those cells. So what he does is he puts on here these little pieces of DNA, and when this DNA goes inside those cells, it produces a protein that basically kills the cells. And to show you how effective it is, this is here on another one of the mice. And what it is he had a whole bunch of mice in which he had tumors, and you can see how big this is. This is about a 2-centimeter tumor here. He injects his drug into the mouse, and I think it was about 6 days later, 80% of the mice have all their tumors gone. And everybody see how this thing shrunk pretty dramatically? And it turns out this works so well that there are 2 drugs already in human clinical trials based on this ligand here. So what it is, they don't have the DNA yet, because that's gene therapy, which is still very controversial. All they did is come up with molecules that go after this protein on the surface of those special vessels. And what it is, Merck Germany has a phase 2 trial for one on brain cancer, and then MetaImmune, which is a US company, has one on melanoma. And I think what it was is in that drug trial, just by going after the protein, even without the gene therapy, they increased the lifespan of people with end-stage melanoma by a factor of 2, which is very good. So, and hopefully with these nanoparticles and the DNA, which kill off the cells even better, and if you do it sooner, it'll work more effectively, because as Brad says, the sooner the better. Now, this is a project here from Bill Trogler, Bob Matry, and also my lab. And what it is this is the idea of trying to combine several functionalities together. And this is sort of the idea here, which is very similar to Dave Cheresh's idea. You would have a liposome here, and then off of this, you would have antibodies to help it stick to cancer cells or to those special vessels. And then inside, what we would have is you would have viruses which selectively reproduce inside of cancer cells. And also you would have ultrasound imaging agent. And the reason for that is if you have ultrasound imaging agent, you can image where the particles go, and you can blow them up in location. Now this is over here from Bob Matry's lab, who's a radiologist at the Cancer Center. And he's been using just simple bubbles that are filled with perfluorocarbon vapor. And this is on a human liver here. And when he puts these in, what it is he can image the vasculature here with these little micron-sized particles. You can see this thing here looks like a tree. And the nice thing is when he can do this, the shape of the vasculature tells him whether it's a benign tumor or a cancerous tumor, so you don't have to do unnecessary surgery. But it shows how easy it is that when you have this perfluorocarbon inside your particles, they are to image. So we want to combine this with the viruses. And the viruses are already being used by Tom Kipps. So Tom Kipps is a leukemia specialist and lymphoma specialist at the Cancer Center. And right now, we're not allowed to put live viruses into people. So what he does is he has a patient here which has leukemia, and he takes the cells out and collects them. And then what he does is he puts these viruses into the cells. These viruses don't reproduce. He just puts enough of them in that what happens is these cells start to produce a protein. And this protein is effective in getting the human immune system to start killing off the leukemia. So what it is the idea is that we take some cells out of the patient, we transform them, and then when we put them back, it wakes up the immune system. And this is a picture over here of, he calls this a stealth cell. This is an antigen-presenting cell, but it's not activated yet. And then this is his virus that he puts in, the adenovirus CD154. And then when this virus goes in, it starts to produce a protein inside there. And then what happens is it's transformed into this guy, which he calls an alarm antigen-presenting cell. So this is one that all of a sudden has new proteins on the surface. And when he puts that back in the body, what happens is the immune system T cells not only start to attack it, but this also activates other cells he hasn't taken out of the body to start being attacked by T cells, so he can see that the number of leukemic cells in the patient goes down when he does this. And this clinical trial is going on at UCSD at our cancer center across campus. And this is a project that Brad and I work on having to do with breast cancer. So roughly 1 in 10 women get breast cancer. They virtually all need surgery, but about a third of them need a second surgery because when they start to take the tumor out, they don't know where the tumor stops and the good tissue starts. And so we want a way of actually reducing this. And over here, this is a microscopy image taken from a patient at UCSD. And you can see here these large dark cells are the tumor cells, and the other cells are normal. So these tumor cells actually are relatively easy to see. But the problem is to do this takes many, many hours. They have to close up the woman and then do the studies on the tumor they take out. So we want a quicker way of doing this in situ so the cancer surgeon, right on the spot, can see if they've gotten enough of the tumor or have to go on. So we're making up little arrays like this where we put on little dots here antibodies that selectively bind the cancer cells and some normal cells. And then the cancer cells also have special proteins on the surface, and then we attach quantum dots to those so we can light it up. And then what we do is we combine this with a little miniature camera. So what it is each of these dots here gets its own little lens, so we can image each of these cancer cells onto the sort of chip that you have in your digital camera. And so that's one project. And then the final project is, as Brad mentioned, early detection. So one thing that would be great is to be able to detect a few cancer cells that are floating around in the blood, because it's much nicer to get a blood sample than somebody to go in and take some of your tissue out. And what it is Mike Keller of our bioengineering department basically has a method that's similar to the Californians who used to pan for gold. So it's an electrostatic method. So basically he applies high frequency electronics to these electrical pads here. So these are electrical pads, and he applies high frequency to these, and he flows whole blood through. And can you see here how the red blood cells concentrate at the center? So if he has a mixture of red blood cells and bacteria are white, he can separate out the red blood from the E. coli. He can wash these away and retain the E. coli. And over here, he's done the same trick where he separates out different types of cells. And so the idea is that he can use this technique to separate out a trace amount of cancer cells that are floating in your blood compared to normal cells based on their electrical properties. And that's it. And thank you for your patience.